Welcome to Learning Chemistry with Faye. In this video, we will go over the steps to draw a Lewis dot structure, and then we will learn how to determine polarity of molecules. First, let's take a look at what is a Lewis dot structure. Lewis dot structure is designed by Gilbert Lewis in 1916, and the element symbols represent the nucleus and the inner shell electrons. The dots represent the valence electron. And as we remember, we can count the valence electrons based on their position in the periodic table. For example, beryllium is in the second column. Skipping over the transition metal, carbon is in the fourth, and fluorine is in the seventh column. And that's how we determine the valence electrons of these elements. So here is an example of how does Lewis dot structures representing the ionic compounds. So the electrons will transfer from one element to another, and the elements are joined together by the force of the opposite charges. So in this case, the sodium is actually giving up its electron to give it to the chlorine, and that way it will naturally form a positive charge, and while chlorine forms a negative charge, and they are bonded together with the invisible force of ionic force. But sometimes both elements desires the extra electrons so they can fill 8 electrons in their valence electron to fulfill the octal rule. So in this case, what they do is instead of transferring electrons from one element to another, they will actually share the electrons. And this is the way that they're represented. They've simply been joined together by 2 electrons, and then both of them can actually fill the electrons together, with each element fills all 8 electrons in their valence electron. In their valence electron shell. And we can sometimes also, by shortening the 2 electrons, by representing the electrons with a bond. So we simply put a dash, and each dash represents exactly 2 electrons. So let's take a look at an example. So in here, we have PF3. What first we would like to do is actually counting all the electrons, the valence electrons of all these elements. With the fluorine, we already know it's a halogen. It has 7 valence electrons in the outer shell, while P has 5 electrons in the shell. So therefore, we will add 5 to 3 7s to get a total of 26. Once we get the numbers of the valence electrons total for this particular molecule, and then we can move on to draw the structure. And in this case, we will go ahead and draw out all the electrons, and its total of 28. Once we draw all the valence electrons around each of the atoms, make sure they are actually they fulfill the octal rule by having 80 electrons surrounding each of the atoms. Then we can also match this number. In this case, it is 26. Once they matches the valence electron numbers that you calculated, you know the structure is correct. And then now you move on. Now we can move on to another example. Over here, we have COH2. So in here, we can also we always start with calculating the valence electrons of the entire molecule. So here we have hydrogen, and then we have 2 of the hydrogens. and then we add it to the carbon, and then we add it to the oxygen, which is 6. So here you have a total of 12 valence electrons. So remember, you wanted to satisfy the octa rule with the exceptions of H. Hydrogen only needs 2 electrons in its valence shell. So that means we only need to have hydrogens have 2 electrons on its valence shell. So what we do is we dot everything according to the octa rule, with the carbons having 4 around it, with the oxygen having 8, and the hydrogen having 2. And we can quickly feel that the carbon and the oxygen, so in this case, if we just drawing all 1 electrons surrounding the carbon atom, our oxygen is missing 2, and our total number of electrons only have only have 12. 2, 4, 6, 8, 10, and 12. Although the carbon in this case have the correct number of the electrons, our oxygen does not fulfill it. So what we will do is we will switch these 2 electrons, and then we will move them over here to create a double bond, with our final structure look like this. We can also, of course, simplify it with the bond structure. Of course, those are dots. And now you, of course, wanted to count all your valency electrons in your structure to make sure it matches the valency electrons that you have calculated for the entire molecule. If they match, then that is the correct structure. In this case, we have 2, 4, 6, 8, 10, and 12. So remember, the only reason that this structure is incorrect is because while your carbon has 8, fulfill the octa rule by having 8 electrons in the valence shell, your oxygen does not. So make sure you actually match it up and for all your atoms to fulfill its valence shell rules. All right. Okay, let's move on to the next example. Let's go ahead and go over another example. So in this case, you have selenium fluoride. So you have 1 selenium and 6 fluorine. So what we started doing, of course, we always start with counting the valence electrons of the entire molecules. So we start with selenium, which has 6, and we have 6 fluorines. And fluorine is a halogen, so we know it has 7 valence electrons, and then we count them together. And in this case, we have 48 of valence, total number of valence electrons for the structure. So where we start next, remember the molecule on the left, the molecule structures is not there to confuse you. So the center atoms is always written on the left. So you first put the center atom in the center, and then you write the rest of the molecules around it, right? So this is how I just naturally write them in the planes to be x and y axis. So it's like this is my z, and this is, of course, one of them is x, and this is its y, or you can count as this is x, y, and this is x, y, and z, right? So once you finish that, you can fill in the electrons with 6 each. I'm just gonna draw a quick dot this way. So, and now of course you can see all the end product right on the right-hand side, left-hand side, I mean. Okay, so once we finish, we wanted to count all the electrons or valency electrons in this particular structure to match the number of the valence electrons that we have calculated. So in this case, each one of them, remember, have to fulfill the octal rule except your center atom. In this case, is expanded. So you have 8. So you have 6, 8. So 6 times 8, you will also have the number of 48. So now that your structure with all the electrons that you have drawn on it matches the number of the valence electrons that you have calculated, 48, then you know your structure is a correct valence, a correct Lewis dot structure. Okay, let's go on to see how do we determine the structures of these molecules. We have a page of giving you the number of electron domains. So now you know how many electron domains that this particular structure, the total number of electron domains that it has. So total number of electron domains, that means you have the lone pairs and the bonding pairs domains, right? So remember, double bonds and triple bonds count as one domain. So in this case, once you have the number of total electron domains in your structure, you can go ahead and predict its structure. And here are the structures you can figure it out what kind of structure that you have with the total number of electron domains, while determining the structure with how many lone pair exist in your particular structure. So for example, if you have a total number of 2 electron domains and you have 0 lone pairs, your structure is mostly linear. So if you have a total number of 4 electron domains and then you have 1 lone pair, then you will have a triagonal pyramid. Or if you have 2 lone pairs with a 4 total number of the electron domains, you will have something that's shaped as bent. All right, and here also gives you the angles of these between the bonds. All right, so with that, we can also, so now we know how do we draw the shape, how do we determine the electron, how do we determine the structures. We can take a look, how do we determine the polarity with the electron negativity values in these structures. So these molecules have a pattern according to the periodic table. And of course, there's many exceptions to the transition metals, but even with that, it kind of follows this pattern decently, okay? So in this case, we have increasing electron activity to the right as they progress, and they have a decreasing electron activity as they go down. So that means once they are going down, the structures, the size of the molecules gets bigger, they become more stable. Of course, as you guys remember, the more reactive the molecule is, the more electron activity it has. So it decreases the electron activity as it goes down the periodic table, and it increases the electron activity as it goes to the right of the periodic table. Okay, and here is how we determine this. Here is how we determine what kind of electron activities does it have. So if it has, so electron activities can be determined by ionic bonds, nonpolar covalent bonds, or polar covalent bonds. Once it reaches a particular electron activity, it basically separates. The electron is not just being shared, but it's being pulled off of one of the elements and transferred to another. And these are the roughly ranges of the electron activities between the two elements to form a bond, whether it's ionic or covalent, and these are the electron activities numbers that you wanted to aim for the range, okay? And of course, it shows right over here. And if you look at these numbers are no longer, this is the electron activity chart for the periodic table. These numbers shows the electron activities for that element. That's not the atomic number, that is not its weight, so don't get confused with it, all right? So for example, if you have F and F bond, how do you determine the electron activity? You simply subtract. If they are the same and equal to 0, then you have a nonpolar covalent. And of course, you can do it similarly. Remember, the difference is always the absolute value. So you can use one subtracting the other. You can always pull the bigger number subtracting the smaller number, just make it easier on yourself. But if you wanted to do it the other way, it's totally fine too. But remember, the difference you wanted to take its absolute value, okay? So if it's in the 1.4 range, remember it's a polar covalent, so that means it's polar. And in this case, if it's completely more than 2, it's over 2, and then you have an ionic bond. Rule of thumb, how do you determine the polarity of a particular molecule? If it's not just a bond, you want to look at how symmetrical and identical they are. If they're completely symmetrical and identical, and that's looking at all directions. So imagine you are the symmetry, okay? So you have to look top and the bottom. So top to bottom, if you draw a line in the center, they have to be exactly the same. And then you look at your left and your right. So pull out your left hand and the right hand. So they have to also be exactly the same and symmetrical. And now you're going to compare what's in front of you and what's behind you. And that, if it fits all of those completely in a similar symmetric, okay, so if they're completely symmetrical and they are the same, then they are nonpolar. They're nonpolar. That means that their electron activities pulse exactly the same to all directions, then they are nonpolar, okay? And then if one of them is different, that means that there is one thing in this particular molecule pulse either more or less than the rest of the molecule, you're going to have a polar molecule. Okay, so here let's go ahead and give it an example. In this particular example, we have SO2, and as you guys know, SO2, the sulfur and oxygen, interestingly, can form a resonance structure. So another known structure that you guys are familiar with is the 2 double bonds with oxygen for both sides. And then you can put the extra electron pair on top of the sulfur. So this is also a correct structure, okay? So with that, well, regardless of which one of these that you actually use, the structures that you use, you can find a dipole moment pulls harder to the oxygen. Okay, so that creates a dipole moment with the overall electron activity pulls toward the oxygen. Okay, so that means that you have a electron negative moment to pull toward the oxygens, and then that therefore is a polar molecule. So in this example, sorry, I pulled the slide slightly faster than I should have, but here's the selenium fluoride. And as we have already drawn the structure, you can see that the selenium is equally centered with 6 fluorine, and no matter, so this one actually forms octahedral structure. And with that particular structure, no matter how you look at it, you can look at every single axis. So you can pull this as a Z, right? You have an X plane and then you have a Y plane. And no matter which plane you're actually looking at, it's pulling exactly the same because it's all fluorine, right? So it actually pulls all direction completely identical in an identical manner. So in this case, you have a compound, you have a molecule with no overall dipole, right? Unless there's a special dipole moment that all the electrons flood into one particular spot. But otherwise, you have no overall dipole. It's completely symmetrical in every way. So in this case, we categorize this particular molecule as a nonpolar molecule. All right, so that is the end of our video, and hopefully this video has helped you to understand the topics of how to draw a Lewis dot structure and how to determine the polarities of a particular molecule. Okay, all right, I will see you in the next video.